Hello everyone, let's solve some Leetcode today. So today we have Leetcode 3 sum, which is one of the most popular problems after 2 sum problem. In this problem, we will be given an array and we need to find the triplets whose sum is basically 0. So you will be given an array like this and you have to find the triplets, basically a set of 3 elements whose sum is 0. So for example, minus 4, then we have 1 and then we have 3. So minus 4, 1 and 3, if you add them, they will result to 0, right? And currently this is the only triplet that we have in the array, but we can have more. We can have multiple triplets, and that is why we are going to send a list of these kind of triplets. So how do we solve this problem? Well, one of the brute force way to solve this problem is to find all the triplets. And so what is a triplet? A triplet is nothing more than a set of 3 elements A, B, C, right? So it means we just need to find all the possible set of 3 elements that we can create from the given array. And how we can do that? Well, we can do that with the help of nested for loop. We will have a for loop here with I, right? Then we will have another for loop here with J, and then we will have another for loop here with K. And in the K for loop, you will have access to I, J, and K. And then you can just check each and every triplet whether the sum of that triplet equal to 0 or not. If it is 0, you simply append or add this triplet into the result list. So you will simply do rest.append and the triplet. But this is not a very optimal way to do this. For instance, the time complexity is what? Order of n cube, because you are having 3 loops, so the time complexity is very high. Plus in the question it is already instructed that we cannot have duplicate triplets, and this way will actually give you duplicate triplets, and it will be very hard for you to actually maintain whether you have duplicate triplets or not. So can we do better? Can we do actually a better solution with better time complexity and easier implementation? Well, yes, we can. But before we go ahead, let us understand how we can actually avoid duplicates. So for example, here we have 4, then here we have 3, and then here we have 1, right? So one of the triplets is minus 4, 3, and 1. So this is a triplet, and if you add minus 4 with a 3 and 1, it will result in 0. So it's okay, it's a valid triplet, correct answer. But then again, we have minus 4, okay, then we have 1, and then we have 3 again here. We will have a minus 4, 1 and 3. So we actually have a duplicate scenario again, right? This is actually a duplicate. We just change the order of these elements, but it is still a duplicate, right? So this is the type of situation that we are supposed to avoid. Now let's make it a little bit more interesting. If I remove 0 here and I add minus 4 again, then what? Well, earlier you were using this 4 to actually make these two triplets, right? But if you actually shift the pointer now, this element is also 4. So this element will actually create its own triplet with 3 and 1 and with 1 and 3. So it's going to have its own two triplets, right? Minus 4, 1, 3 and minus 4, 3, 1. So it means we actually end up having the same triplet 4 times, and we don't want that, right? So to understand how we can avoid duplicates, we need to understand how the duplicates are formed in the first place. So if I just go ahead and actually remove the 0 and add minus 4 here, and we actually remove 1 and 3 also here, just for the simplicity sake, we will add them later on. So right now we have a 4 here, okay, and I want to make triplets. So I will have 4 here fixed, okay, and then I will go through these elements, right? So in the remaining elements, I found 1 and 3 to be the elements that I add with 4, and they will give me a result of 0, right? Great. And so we append this into our result variable. Now this 4 is done, okay, we try to find all the possible triplets with this 4. Now we will actually shift to this 4, okay. Now this is the 4 that we are dealing with, and this is the remaining set of elements that we will have to actually get the remaining elements from. So in this remaining set, we again get these 1 and 3, and then we again end up making minus 4, 1 and 3 triplet. The reason this happened is because we use the same element minus 4 again in the next iteration to find the triplets. What we should have done is we should have skipped this minus 4, right? Because minus 4 element is already done. We have found all the possible triplet with minus 4, so we don't need to do that again. So better thing would be to just skip the minus 4 and go to the 2, and this would actually result in a new triplet if there was any. So what we need to do is we need to skip the duplicate elements together, right? We will take minus 4 only once, and then we will skip all the rest of the instances and get to the new element or the new number. But remember that in our array, we can actually have minus 4 here, then 0, then minus 4, then 1, then 3, right? So if we are at this position, we have no way to find out that there is another minus 4 outside, that we have another minus 4. So what will happen is that we will end up using this minus 4 to create triplets with 1 and 3. Then we will shift to 0, we will not have any triplets. Then we will shift to this minus 4, and we will end up creating again the same duplicate triplet. So how do we solve this issue, right? Well, we can only solve this by sorting it. So sort this thing so that all the same elements minus 4 will be together, and then you can actually go ahead and skip those elements altogether. So we have sorted the array, we have all the common elements together. We will now be able to avoid duplicates. So our duplication problem is solved. Now how do we solve this order of n cube time complexity problem? I would like to reduce this time complexity somehow. So in order to reduce this, we need to observe our original brute force solution. In the original brute force solution, we were actually having for loops, right? We had 3 for loops, and then we were just getting these I, j, and k to create the triplets, right? But if you would have solved a 2 sum or 2 sum 2 problem, you would know that we can take these 2 for loops and just convert them into a single for loop. Yes, we can do that. We will have a for loop here. Okay, we will have I index. So this for loop will start from here I, and then we will actually use two pointer technique. So we will have an L pointer here, and we will have an R pointer here. And then we can simply have a while loop inside of the for loop, and we will have L less than equal to R. So while L less than equal to R, we will run this while loop. Now in the while loop, we are going to check if the sum is actually equal to 0 or not. So suppose that we have 4, we have minus 4, and we have 3. So what is the sum of minus 4 and 3? It is minus 5, right? So minus 5 is what? Minus 5 is less than 0, correct? If it is less than 0, we need to find a way to increase the sum, right? To increase the sum, what we can do? I is fixed. I is going to be at this position. So the only thing that we can move is L or R pointer. Since it is less than 0, we need to increase it, right? So currently in our triplet, we have minus 4, then minus 4, and then 3, right? This is fixed. So we have to move this or this. So we found a pair of two elements that we are dealing with. That's why we are using two pointers here. So we will take this minimum element and we will increase it so that the overall sum will increase. So I will take the L pointer and I will increase it to 0. Now what is the sum of minus 4, 0, and 3? Well, it is minus 1. So our sum is increased from minus 5 to minus 1. Great. But it is still less than 0. It means we still need to increase the L pointer. We take it here. Great. Now we have minus 4, 1, and 3. The sum is going to be 0. So we found a triplet. And we will add this into the result variable. So one of the triplets we have found. Great. And the reason we were able to actually increment L is because this portion, okay, this entire thing is sorted. Do you understand it? We have a sorted array at this point. That's why we were able to increase L, because we knew if we increase L, we will get a bigger number, and that bigger number will help us increase this overall sum. In the same way, we can decide to decrement R, because we know that if we decrement R, we will get a smaller number most likely, and that smaller number will actually help us to reduce the effective sum. So now I believe you are able to see why we are using two pointers. We are using two pointers because we have sorted condition, we have a linear data structure, we have pairs. We are dealing with pairs of elements. So that's basically a recipe for two pointers. But currently we are at 1 and we are at 3, right? We found that the sum was 0 at this point. So which pointer should we move? Should we move L pointer or should we move R pointer? Well, we can move any pointer because we need a new triplet, right? So if I try to move L, L will be at 1, right? It's a new index. The value is still the 1, but the index is new. So we will end up adding minus 4, 1, and this 3. This will again result in the same triplet. It will again give us 0. We will again end up putting the same triplet in the result variable. That we do not want to do, right? It means once we found this one, we need to skip all the remaining ones. Okay, so we will skip all the remaining ones and we will come to 3. Then 3 plus 3, then plus minus 4. What is this? It is simply 2, right? It is greater than 0. So we will end up shifting R to this 3. So R is now here. L is also here. So L and R are actually at the same position. So L basically is equal to R. So we will end up stopping this while loop, and then we will increment this I. Now we found the I to be minus 4 again, which is basically equal to the previous value. So we will simply again shift it to this one. So I will here, and then we will again go through this entire remaining set. And in this way, we will end up going through each and every element, and we will find all the possible triplets. Now, all of this may seem a little complicated, but let me tell you, if you know how to solve two sum, and if you know how to solve two sum two problem, this problem would be very straightforward. So I would highly recommend you to solve two sum and two sum two problems if you want to get a better understanding of this problem. So in essence, what we did is very simple. We just avoided duplicate by shifting through the entire range of the same elements, correct? For both I variable and for L and R. Now let us go through the code. We have the result variable in which we will store all of the triplets. Then we are sorting the given array so that we will have all the common elements together so that we will be able to skip the elements to avoid duplicates. Then we have the for loop. We are enumerating over the nums array and we have this index and the element a. So I represent the index and a represent the element. So if the I is greater than 0 and the element a is same as the previous element, we will continue. So we are going to skip the entire range of the same element. Now we are saying I greater than 0. Well, if it was 0, we would actually be at the negative 4 for the first time, and in that case, we would actually like to run this entire loop and get all the triplets with negative 4. So that's why I greater than 0 here. So after skipping the duplicates for I, we will have L and R pointer. So here L is equal to I plus 1 and the R is equal to the ending element. So we are running while L is less than R, we are calculating the three sum. So the element A plus the element at L plus the element at R. If the sum is basically greater than 0, we know that we need to effectively reduce the sum. We know that we have to effectively reduce the sum to reach 0, right? That's why we are reducing the R pointer, because we know that the array is sorted, and if we reduce the R pointer, we will get a smaller element. Otherwise, if it is smaller than 0, we will increment the L pointer to get an effectively bigger sum, the bigger three sum, because we know the next element to L will be bigger than the current L. Otherwise, if it is neither too small nor too big, we know that we have found the sum to be 0. In that case, we will simply append this triplet into the result variable. Remember that we are not appending the indexes, we are appending the elements. So A is an element, nums of L is an element, and nums of R is an element. That's what we are appending to the result variable. And then we are only incrementing the L by 1, and then we are skipping all the duplicate L's, just like we had L here, and then we are skipping all of these ones. Then we will reach 3, and that is what we are checking here. If the current element at L is basically same as the previous element, then we will simply increase the L pointer by 1. And also we need to make sure that L never becomes bigger than R. So we have this condition while L is less than R, and this condition will also help us to decrement R pointer automatically. So for example, suppose that L was here, we will check, is the current element same as previous element? Well, yes it is. So we will increase the L to here. We did not do anything to R, right? But in the next iteration, in the entire loop, something will happen. So suppose that I was actually not -4, it was -1. Okay. So currently we are trying to find the triplet of -1, then L, then R, right? Now currently the L is at 0. So we will sum -1 plus 0 and the R is at 2, correct? So we will have like 1, which is bigger than 0, right? In the next iteration, this is what we will find. So we will simply end up decrementing R automatically here. Then again, this is basically duplicate of this one, right? Then again, the same condition or the same result will happen in the next iteration. Then again, we will end up basically shifting R to this side. And then we will have like 0 here. And since they are at the same position, we can simply end the loop. So we ended up skipping the duplicates for R pointer automatically. We just had to manually shift the L pointers properly. That is why here we are only shifting the L pointer properly, because the R pointer will be shifted if needed to be shifted in these conditions in the next iteration automatically. And once this entire thing runs, we will simply return the result variable. So now let us try to run this thing and see if it works. And so yeah, it works. Our solution runs in 525 milliseconds, beats 74.73% of the solutions on Leetcode. So it's a pretty efficient solution. Now let us talk about the time and space complexity. So the time complexity will be order of n log n, because we are sorting. Okay, so sorting steps gives us order of n log n, and then we have two nested loops, for loop and then while loop. So that will actually end up giving us order of n square time complexity. So overall, this is far bigger than this. So we will simply say time complexity is order of n square. That's it. Now the space complexity is what? Well, space complexity can be order of 1 or it can be order of n. And this confusion is arising because of this sorting step. So in some languages, you can actually have functions that will actually sort the array in place. That means they will not use any extra memory. So at that time, we will have order of 1 space complexity. But in some languages, they may actually use extra space to actually sort the array. So in that scenario, the sorting function in that language will take order of n space, resulting in order of n space complexity. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.